All right, good morning, everyone, and welcome to our live event this Friday morning. We're really excited that you're here with us, and we're excited to be hosting our guest speaker, Justin Bartel, from the Science Museum of Virginia. He's an astronomer there, and he works in their planetarium to explain a lot of things about space, but mostly asteroids. He knows a lot about asteroids. We're really excited to have his expertise here for our presentation today. Well, I'm Dana Thompson, the director of the Brown Planetarium at Ball State University. And if you haven't been before, here's a picture of the outside, but more interesting, let's go ahead and see the inside of it. In the Brown Planetarium at Ball State, we have a 16-meter dome. So we have projection technology in the center here. We have an analog, or really more accurately, an optomechanical projector. But we also have digital projectors, and you can see the light coming from one of those digital projectors down here, and it's projecting onto the dome, this 52.5-foot dome, all over on every single piece of it. So we can create visualizations on the entire dome using our projection technology. We seat 152 in our planetarium, and we would love to be giving this presentation in our planetarium, but we have the next best thing, because Justin actually is going to be using his software that he uses in the planetarium at the Science Museum of Virginia to be doing the program today. So you can see all the way in the back of our planetarium, we have the controls back here. That's where our presenter would usually be controlling the system, controlling all of the technology in the planetarium to be showing amazing content on the dome. And Justin has his planetarium software up and running and ready to teach us all about asteroids today. So I'm going to go ahead and stop sharing my screen and turn it over to Justin for the presentation.
All right. Well, good morning. Thank you, Dana. Happy to be here, and yeah, of course, happy to share what I think is very interesting information about asteroids with you today. So let me share my screen so that everyone can see the software here. And we're just going to start out with a view of the Earth, because well, when do you usually hear about asteroids in the news these days? Well, it's if one is getting close to our planet. And I found a couple of them for you that have been in the news recently. So let's put their paths through space on the screen here. I've added the orbit of the moon to the screen for you as well. Way back at the end of April, almost exactly 1 month ago, the asteroid named 2020 HS7 followed that kind of orange path by the Earth. Then about a week later, on May 4th, another one called 2020 JJ got much, much closer. And it followed that red line. And you can see just how close that one got to the Earth. So it'd certainly be something worth keeping an eye on. Now, if either of these had hit, it wouldn't have posed any danger for us here on Earth. They're both really small, and really they needed to be this close to the Earth for our telescopes to be able to see them. But of course, there are bigger asteroids out there, so we want to keep track of them. We want to know where they are, just so that one doesn't catch us unaware. You can certainly ask the dinosaurs what happens when a big asteroid hits. So that's certainly one reason to keep track of these things, but I think they're pretty interesting all by themselves. They have interesting stories to tell us about our solar system, so that's why I really keep track of them and love sharing them with my audiences. And before I get into any of those stories, I do want to cover some basic ground with you about asteroids. First, let's talk about those names. I threw a couple of strange, almost code names out there that may have sounded like license plate numbers. Those are the kinds of designations that asteroids get when they are first discovered. Let's go to that one in red, because that's a little bit easier to explain. It's 2020 JJ. 2020 is just the year that asteroid was discovered, so it was found this year. That first letter tells us what time of year it was found, and J represents the first half of May. Then that second letter tells us what order it was discovered in within that time period. So J is the ninth asteroid. So 2020 JJ is the ninth asteroid discovered in early May of this year. All right, let's go to 2020 HS7. Added an extra character there at the end. You'll sometimes see it as a big letter, but it's technically a little subscript. But it works the same way. H is the time of year. It's the last half of April. S is the order that represents the number 18. But then that number 7 means it's not the 18th asteroid discovered in late April. You have to go through the alphabet 7 times. It's counting 25 letters each time. They leave the I out. It looks too much like 1. So that means 2020 HS7 was, let's see, 25 times 7 plus 18. I'm sure you've already figured it out. That is 193. So it's the 193rd asteroid found. Now this already reveals some interesting things about how we find asteroids. If you look up some of these asteroid designations, you'll see that sometimes that number at the end is 3 digits. So you've got to go through the alphabet hundreds of times. So sometimes we're finding hundreds of asteroids in just a 2-week period. So there are a lot of them out there. Sometimes it's a little bit easier than this, though. This is just what they get at first to help astronomers keep track of them. After a while, once you really know how the asteroid moves around the sun, you can go ahead and give it a regular name, a word that we can use to identify the asteroid. And there are some 23,000 asteroids that have these slightly simpler names. Now, there are of course, some rules involved here. The names are approved by the International Astronomical Union. They're the folks that keep track of lots of rules for astronomers. And the rules for naming an asteroid are fairly simple. They prefer one word. They would like the one word to be 16 characters or less. They try and stay away from commercial names. You see a lot named after people, some just other astronomers, historical figures certainly as well. But there are a few kinds of names that you aren't supposed to give. And I thought I would single out one of them here. On your screen, hopefully you're seeing Mr. Spock highlighted there. Now, I know what you're probably thinking. It was named after the sea turtle that was featured in this presentation a couple of weeks ago. Or maybe it was named after the famous Star Trek character. But both guesses would be not quite right. The astronomer that found this asteroid way back in 1971, he had moved around a couple times. That happens in astronomy sometimes. And Dr. James Gibson decided that he would name this asteroid after one of his only companions on all of his journeys, his pet cat. See, his pet cat, he realized, was imperturbable, logical, intelligent, and of course had pointed ears, just like the Vulcan that we all know. So that's what he named his cat, and then he named the asteroid after his cat. For some reason, the International Astronomical Union wasn't all that fond of that. So now one of the rules is you can't name asteroids after pets. So there we go. But they've come up with many interesting names for asteroids in the meantime. And it wasn't always so complicated. There weren't always so many rules, code names for asteroids. All of this started in a much simpler time with an astronomer named Giuseppe Piazza. He's got an asteroid named after him too. But let's go back and look at his story. So this is the solar system as we knew it in the late 1700s. And astronomers thought they'd figured out some kind of interesting things about the solar system in those days. First, they thought they knew how planets were ordered or how they were spaced out in their orbits around the sun. They thought there was some basic rule that explained all this. You might see it called Bode's law sometimes, although there was really another astronomer that came up with the idea first. So you might see it called Titius Bode's law as well. And that just said that each planet is at a distance from the sun that can be described by a simple equation. It's Friday morning, so I'm going to do the actual math for you. But here are those distances that astronomers thought the planets should be spaced at. You can see Mercury, it's pretty close, but on average, it's on that dashed circle. Venus and Earth, almost perfect. Mars, again, pretty close most of the time. There seems to be something missing just outside the orbit of Mars. Then we've got Jupiter, its orbit pretty close to another dashed circle. And then there's Saturn out there too. So all of the planets we know about in the solar system in the late 1700s seem to follow the rule. And then in 1781, Uranus is discovered by William Herschel, and its orbit also followed that rule. So if a newly discovered planet is going to follow this kind of strange mathematical rule, that makes some astronomers kind of look again at what's going on between Mars and Jupiter. Why does the rule predict something is there that they can't find? So a team of astronomers got together and they decided to search for what had to be a missing planet between Mars and Jupiter. This team of astronomers called themselves the Celestial Police. As they were getting organized, they sent invitations all across Europe. These were all European astronomers. And one person they invited to join their search was Giuseppe Piazza. Now, he hadn't gotten his invitation yet in early January, in fact, January 1st, 1801. He was just cataloging stars in the constellation Taurus, but he noticed a star that seemed to kind of move among the others in his telescope's view. He watched it for a couple of nights and thought, I must have found something interesting, but he couldn't quite figure out what it was. And he started spreading the news to other astronomers. And stop me if you've heard this story before. There's this newly discovered object where astronomers think they're going to find a planet, but it looks a lot smaller than they were hoping for. The astronomers start arguing a lot about what they should call this thing. Is it a planet or is it not a planet? Is it something else? They kind of argue about what name they should give it. Then in the meantime, other astronomers continue looking at the sky and they start finding more and more objects in the same part of the solar system. The same thing kind of happened to Pluto. But this is the story of Ceres. And the Celestial Police keep searching. They find Juno, Pallas, and Vesta, more asteroids in the same part of the solar system. After a brief delay in the mid-1800s, astronomers start finding more and more of these little worlds. And I'm going to start adding their orbits to the screen for you as well. Now, for the most part, these asteroids, these little worlds, are mostly contained between the orbits of Mars and Jupiter. But eventually, some oddities start to show up. In 1898, an asteroid named Eros is discovered. Its orbit is highlighted blue in the inner solar system here. And you'll be able to see that it gets pretty close to the Earth. So it's the first example of what we now call a near-Earth asteroid. The two I showed you at the very beginning of the show, definitely near-Earth asteroids. They got pretty close. Then a few years later, another kind of strange one shows up. Out here near the orbit of Jupiter, there's an asteroid named Achilles that takes the same amount of time to get around the sun as Jupiter does. Turns out to be the first of another kind of class of asteroids that we call Trojans that sort of follow planets in their orbits around the sun. There are thousands of them that orbit with Jupiter. Then another few years later, another kind of strange one pops up. Its name is Hidalgo, and it goes out past the orbit of Jupiter, but it isn't one of those Trojan asteroids. It was kind of unique for a while, but eventually we found many more that crossed the orbits of the gas giants in the outer solar system. So the discoveries continue, and the orbits that are appearing on the screen for you now are just the first 5,000 asteroids to be found. And it took almost 200 years for astronomers to find these 5,000 asteroids. We're running up to the year 1991 here in the simulation. But of course, we found many more asteroids today. And if you check out the current catalog, the IAU Minor Planet Center now lists almost 1 million asteroids in the solar system. So of course, the pace of discovery has picked up. A couple of things have helped with that. In the 1990s, astronomers, like many of us, started using digital cameras, and those digital detectors allowed them to find smaller objects and analyze the images with computers instead of just studying photographic plates. And so they started finding more and more of these objects, and that's how we have found almost 1 million of them today. That's how we can find hundreds of them in a 2-week period. And we found that now these little objects are everywhere in the solar system. I'm going to put a not quite complete map of their orbits on the screen for you, and hopefully your entire screen turns green, but you might be able to pick out a couple of the patterns here as well, like the main asteroid belt in there. Because there are so many overlapping orbits in the software here, it ends up looking bright white. Then there are a lot of green orbits kind of crisscross with the outer planets. And then there's another much brighter band. That would be just outside the orbit of Neptune. That is the Kuiper belt. And then there are some little objects, or as we might call them, minor planets, that travel even farther from the sun, well beyond the Kuiper belt. And these are all interesting worlds. But as the patterns have kind of come into focus, astronomers have started using a little more careful language to describe them. So in the 1800s, when they're first found, they kind of settle on the word asteroid, and all of them are asteroids for a little while. But now that we see that they move in different parts of the solar system, and we can sort of group them in different ways, we now have different names for these little worlds in different parts of the solar system. So usually when you hear somebody talk about an asteroid, it's something at or inside the orbit of Jupiter. Then those objects that cross the orbits of the gas giants get called centaurs. If you know what centaurs are in mythology, like half horse, half human. And centaurs in astronomy are like half asteroid, half comet. So a lot of times they just kind of look like asteroids, little dots in telescopic images. But sometimes they grow atmospheres and tails like comets do. Then we've got the Kuiper belt objects out here. And there's even another group that I didn't put on the map, but the ones out beyond Neptune that are not part of the Kuiper belt are sometimes called trans-Neptunian objects. So lots of interesting worlds with interesting stories. Each one of these groups has interesting representatives, and so what I like to do is look for interesting discoveries or interesting stories to tell, and share them with as many people as I can as part of an ongoing Planetarium series. I'm about 70 episodes in, but working on 1 million of Better Know an Asteroid. And so there are many of these asteroids that I think we should take a closer look at, because they can show us strange and fantastic things that happen in the solar system. Take, for example, one relatively new asteroid in our catalog. It goes by the designation 2020 CD3. So you probably already know enough to decode that. Let's see, it was found on, it turns out to be Valentine's Day of this year. It is a near-Earth asteroid. I'm going to show you just how close it gets by going backwards in time just a little bit here. We're looking at the Earth, the orbit of the Moon, and here comes 2020 CD3. Now, we're going backwards in time, remember. So when astronomers first spotted it, it was on the left-hand side of that dark red line. It was actually moving away from the Earth. But just using the laws of physics, the universal law of gravitation, you can calculate where that asteroid had been. And working backwards in time, astronomers have rebuilt its trajectory and found that this little asteroid was actually in orbit around the Earth. It may have been in orbit around the Earth for a couple of years, but because it's thought to be pretty small, maybe a few meters wide, about the size of a car, it had to be really close to the Earth for us to find it, and it just happened to show up on Valentine's Day, when it was relatively close to the Earth. But it had been there since perhaps 2018, 2017. We don't know exactly when it entered orbit around the Earth. May have gotten a little help from our own more permanent moon to slow it down as it was flying by the Earth and get captured by the Earth's gravity. It spent most of its time very far from the Earth, and at those farther distances, the Earth's gravity is a bit weaker. And so even the gravity from our own moon and the sun really affected how the asteroid was moving around the Earth. So that's why its orbit kind of jumps around there a little bit. And that's why we can't be entirely sure what its orbit looked like for the whole time it was in orbit around the Earth. I'm sorry to say that it is gone now. It escaped Earth's gravity altogether back in early May, the first week of May. So we're back to having just one moon, but for a while there, whether we knew it or not, you could say the Earth had a couple of moons, at least 2 moons. And that may actually be a normal thing. We may capture asteroids from time to time like this. Astronomers have only spotted this happening a couple of times in the past, so you'll only find a couple of other temporary moons like this on the record books. But again, because they're small and they're usually kind of far from the Earth, we just may not be able to see them. So they may be out there. Earth may capture little asteroids all the time. So that kind of makes a fuzzy distinction between what's an asteroid, what's a moon. You know, if we capture an asteroid, is it still an asteroid? And it can be kind of hard to classify these little worlds. So let's look at another example by transitioning to another little asteroid in the solar system here. I'm going to back away from the Earth, show you the inner solar system. I'll add the orbits of the planets to your screen. And then we're going to take a closer look at one of the earliest asteroids discovered. It was 10th out of the 1 million or so that we have found. Its name is Hygiena. Now, it is in the main asteroid belt between Mars and Jupiter. And one reason astronomers spotted it so early is that it is pretty large. To give you a sense of scale here, we've got the Earth. We've got a circle. I tried to center it on Muncie for you. It shows the size of Ceres, and then Vesta and Pallas, 2 of the other early discoveries, and then Hygiea not too far behind in terms of size. We now think it is the 4th largest object in the asteroid belt. Its orbit shown in green here, a little bit farther away from those other big ones, Ceres, Pallas, and Vesta. And so that's made it kind of hard to observe Hygiea until now. There's a new telescope on the European Southern Observatory's Very Large Telescope. It's called the Sphere camera, and it takes really high definition images of small objects in the solar system. You can see a real picture of Hygiea there. And to give you a sense of what's being revealed in the image, a sphere picture of the asteroid Vesta compared to a model of what the camera should have seen based on data from the Dawn spacecraft that actually orbited Vesta. So it's not a crystal clear picture, but it's enough to pick out major features like craters and things like that. And with multiple pictures, you can actually build a model of what shape Hygiea is. And it looks like it's very round. In fact, if we compare it to a perfectly spherical object, you can see that Hygiea is very, very close to being round. So that actually may qualify it as a dwarf planet in the solar system. Another interesting thing about Hygiea is that it has a family. A lot of other asteroids, much smaller than Hygiea, that orbit the sun on similar paths. Now, that's not uncommon, and we think that happens because of collisions. Now, collisions are fairly rare among asteroids, but given 4.5 billion years and millions of asteroids, a few are bound to run into each other. And if Hygiea had suffered a massive collision that perhaps vaporized the first version of Hygiea, it would have thrown a lot of debris out across the solar system and could have become the Hygiea family of asteroids that we see today. Then the nearly molten Hygiea would have been pulled back together by gravity. And because it was a fluid instead of a solid object, gravity could have shaped it into a sphere, perhaps reaching what's called hydrostatic equilibrium. That's just a fancy scientific way of saying it's round. So being round and then being in a crowded part of the solar system is all it takes to be a dwarf planet. So maybe that's what Hygiea is. So again, we're kind of blurring the lines between what these objects are and how we classify things. Is Hygiea an asteroid or a dwarf planet? A little more study might be needed. But there's another object that kind of blurs the lines between what's what. It is a brand new discovery, actually, at least a brand new announcement. It is an object called P 2019 LD2. they've introduced one more new character to that classification scheme, and I'll get to that. But the rest of that code tells you instantly it was found back in 2019. It was found in an orbit that is kind of similar to Jupiter's. So based on what we've seen already, you may instantly jump to the conclusion that it is one of those Trojan asteroids that shares Jupiter's orbit. But this real picture of a 2019 LD2 shows something else strange. It's kind of hard to see. You might just be able to see a thin, wispy tail sticking off to the right. So, all right, it kind of looks like a comet. Well, that can happen. But here's where things really get strange. If we look forward in time, we've got this potentially comet-like Trojan asteroid that is very close to Jupiter, and it gets nudges from Jupiter because it isn't truly in those swarms of Trojan asteroids. So if we look just a couple decades into the future, the orbit of LD2 is going to change quite a bit. It's going to start traveling into the inner solar system. As it gets closer to the sun, we can expect it to behave more and more like a comet. So ask again in a couple of decades, and you may truly see this thing called a Jupiter family comet by astronomers. That's where that letter P came from at the front of the name I showed you a moment ago. That's just how astronomers designate periodic comets that we know come around the sun in a predictable way. And so here's this new object that was first announced as an active Trojan asteroid, is now on its way to becoming a Jupiter family comet. And even more strangely, perhaps, if we go back to the present day, and again, just follow the laws of physics and look backward in time instead, we can see that just a few years ago, LD2 probably encountered Jupiter, a relatively close range, and prior to that, it had been on a much larger orbit that perhaps stretched out beyond the orbit of Saturn. So that's the kind of path followed by one of those Centaur objects that we saw before. So here's another strange thing about asteroids. You may not always be an asteroid. Objects can move to different parts of the solar system over time and move into new categories and change designations, start behaving in different ways. So again, these aren't just plain gray rocks orbiting the sun. These are active dynamic objects that are always changing and always showing the way the solar system works. So if our solar system is lucky enough to have so many of these interesting objects, are there asteroids in other solar systems? Well, good question. And we think we have an answer now, thanks to a discovery from October of 2017. So let's look back in time here. In late October of 2017, astronomers found an object that is now called Oumuamua. And Oumuamua turned out to be moving very quickly in its orbit around the sun. Gravity is again, a fairly simple mathematical relationship that we can do pretty powerful things with. And based on the location and speed of Oumuamua in 2017 when it was discovered, astronomers found out that it couldn't be bound to the sun by the sun's own gravity. So it must have formed somewhere else, and it must have just happened to fly through our solar system. Is moving so fast, we're honestly kind of lucky to catch it. And if we fast forward the couple of years from its discovery to today, we can see that it's already nearly to the orbit of Uranus. Because it's pretty small, only about 400 meters wide, we can't take pictures of it anymore. But the data that was collected when Oumuamua was a little bit closer to the sun has revealed some very interesting things. You already saw its kind of strange shape, which was unexpected. But now we are also perhaps getting closer to figuring out what it was and perhaps how it formed. There was a new paper just released yesterday that suggests maybe this object wasn't made out of rock and metal or even ice like asteroids and centaurs are in our solar system. Perhaps this is something left over, not from the formation of planets in some other solar system, but from the formation of another star. It's a paper that I haven't even had a chance to read all the way through yet, so I don't entirely understand it. But one possibility is that Oumuamua is a giant chunk of hydrogen ice that perhaps wasn't able to fall into a star as it was forming and was doomed to wander the galaxy. So some kind of galactic hydrogen iceberg. If that doesn't get the imagination going, I'm not sure what will. We can't really answer that question for sure about Oumuamua because it's too far away. It's moving too fast for us to see it again with telescopes here on Earth, and none of our spacecraft are ever going to be able to catch up with it. So astronomers are working on plans to kind of park a spacecraft up in space, either a high orbit around the Earth or an orbit around the Sun, to be ready for the next one of these interstellar objects that gets discovered. So we can get a better look at it. It's not just interstellar asteroids we want to study. We've got our own asteroids to keep an eye on too. And I've added a couple of yellow dots to the screen for you. Those are all of the asteroids in our solar system that have been visited by spacecraft. It's only 15. And there are 2 asteroids that are currently under investigation. They are the asteroids Ryugu, which was visited by the Hayabusa 2 spacecraft, which has since departed. It's on its way home with a sample of the asteroid. And then the asteroid Bennu, which is currently being studied by the OsirisRex spacecraft. Both of these asteroids are pretty interesting. And in fact, they may be part of the same asteroid family. That's one interesting thing that these 2 independent spacecraft have discovered. Here are the best shaped models I can give you for these asteroids based on what the spacecraft have found. And they're both kind of shaped like spinning tops, which is kind of neat. They're both also what we might call rubble pile asteroids. It looks like they are composed of lots of smaller boulders and chunks of rock. Now, both spacecraft have studied their asteroids in interesting and unique ways. In the case of the asteroid Ryugu on the left, a little bit larger, about a kilometer wide or 6/10 of a mile, the Hayabusa 2 spacecraft rendezvoused with the asteroid. I started studying it, taking real pictures of the asteroid, and that's how I built we built the model that was in the background for you. You can see some real close-ups of the asteroid. So again, kind of seeing that blocky consistency, lots of rocks of all sizes, big boulders, small boulders, medium-sized rocks, small rocks. And now the ultimate goal of both of these missions is to collect a sample of their asteroid for return to Earth and better study. But Hayabusa 2 took a couple of steps to get to that point. First, it released some landers, little spacecraft it carried with it. There were 2 Minerva landers that descended to the surface of the asteroid, helped scientists better understand what the surface properties were like. Got some real pictures from the Minerva landers coming up on the screen for you. Those even had the ability to kind of hop around on the surface of Ryugu. Little flywheels inside the landers allow them to do that. And then a little bit, yeah, go ahead.
Quick question. How are the asteroids chosen for spacecraft missions? John Straka wants to know.
Excellent question. Well, there are a couple of reasons that asteroids are selected. One important factor is, well, convenience, whether we can get a spacecraft there in a reasonable amount of time or not. And for something like this, a sample collection, you might also want to go to an interesting population of objects or an interesting type of object. You're seeing imagery from another lander and soon the first sample collection of Ryugu. And both Bennu and Ryugu are a part of a group called Apollo asteroids. There's certain kinds of near-Earth asteroids that follow certain orbits around the sun. And Bennu, in fact, is the asteroid with the highest chance of hitting the Earth. Now, we don't think it's going to happen, at least not for hundreds and hundreds of years. But, Bennu and other Apollo asteroids are some of the most dangerous asteroids out there. So if this is the kind of asteroid that's going to hit the Earth, we really want to know in detail what these asteroids are like. If they're loose collections of gravel and boulders, that kind of makes it hard for us to say, do what they did in the movie Armageddon and just blow up the asteroid, right? Then we just have all of these boulders coming at us instead. So that's why we really want to understand what these particular types of asteroids are like. Some other future missions are going to explore other interesting targets, like there's a spacecraft named Psyche that's going to launch in a couple of years. It's going to an asteroid in the main asteroid belt with the same name, and they selected that asteroid because observations from Earth show there might be made almost entirely of metal. So there's a chance that Psyche is the core of a planet that was forming in the early solar system. Maybe it suffered one giant or several large collisions that stripped off the rocky material like Earth's mantle and crust, and just left the nickel iron core behind. So sometimes just interesting objects, unique looking asteroids, or sometimes it's asteroids like Ryugu and Bennu here, which are just the kind of asteroid we need to know more about. The Hayabusa 2 mission has completed its study of Ryugu. It selected a couple of different samples. You saw one sample collection if you're watching the imagery. There was also another one where they released another kind of lander that actually had an explosive charge on it that opened up a little crater on the surface of Ryugu so they could collect material from under the surface of the asteroid as well. So that sample is on its way back to Earth. It is scheduled to arrive at the end of this year. So in December, we should get a little bit of Ryugu on the surface of the Earth. Better to bring small parts of the asteroid to us than waiting for the asteroid to come to Earth all at once. Similar story with OsirisRex at Bennu. This is NASA's first sample collection and sample return mission from an asteroid. OsirisRex has been in orbit around Bennu for a little over a year now, and they are preparing for their first sample collection attempt. Along the way, they have mapped the asteroid in higher resolution than any other world in the solar system on a global scale. So you're seeing the real map of Bennu on the screen, and I could zoom in even more. We can see some tiny little pebbles on the surface of Bennu. We have this really high resolution map over the entire globe. There's some parts of the Earth that we haven't mapped in this level of detail, but we can see all the way down to pebble scale all over Bennu, which is pretty impressive. With that highly detailed map, mission scientists have been able to pick out their target sampling sites, and the primary sample collection site is a little crater in the asteroid's southern hemisphere named Nightingale. And on the left, you see real imagery from the spacecraft of something they did called a checkpoint rehearsal. So they got kind of down to the last point they will get to when they really sample the asteroid, just to make sure the spacecraft could operate correctly at these low altitudes. And because the asteroid is somewhat separated from the Earth, mission scientists aren't going to be able to control the spacecraft in real time. So it's got a program loaded onto it, and the spacecraft is going to be flying autonomously when it actually collects the sample. So they want to make sure that it's correctly identifying itself, correctly orienting itself, finding the landmarks it's going to need to get all the way down, touch the surface of the asteroid, kind of like on the imagery from Hayabusa 2 you saw, where Hayabusa 2 fired a projectile at the asteroid to churn up material. With OsirisRex, they're just going to shoot some nitrogen gas at the asteroid to again churn up some material and catch it in the device at the end of the arm. You can see in the video here. Now, if they collect enough material with this first sample collection attempt, that'll be it. The spacecraft will back away and wait for its chance to return to the Earth. If they don't collect enough, they can collect up to 4 samples from the asteroid. They want to get enough material to do some pretty complex study on it here on the Earth. So that will depart, and it'll take a couple of years for Bennu to get back. The schedule the sample from Bennu isn't scheduled to return to the Earth until the year 2023. And it's worth looking forward to, because that'll teach us a lot more about these rocks. And hopefully now you see that there are a lot of interesting worlds in the solar system. It's not just the sun and the 8 major planets. There's a lot to see out there. Other future missions targeting other interesting asteroids. The Lucy mission is coming up in a couple of years. That's going to head out to fly by several of Jupiter's Trojan asteroids. There is a Japanese mission that's going to target a unique object called the Phaethon that gets really close to the sun and is probably the parent object of one of the meteor showers we see on the Earth. It could be kind of another hybrid object that behaves kind of like a comet in a way, and other missions targeting more near Earth asteroids. But here you go. Here is a more complete map of the solar system. This isn't quite all of the asteroids, but it's enough of the asteroids. It's closer to 800,000 of them as opposed to the 950,000 of them that we have found so far. But I hope the next time that you picture the solar system in your mind, this is the kind of map that you see. Some big, interesting worlds and lots of small, interesting worlds out there too.
That's wonderful, Justin. Thank you so much for taking your time with us today. We do have a few questions, and I'm going to go ahead and switch over to my screen really fast. You can go back to yours if you want to use your software to answer some of the questions that are coming through. But one of the questions is, like, how do we really classify all these things when there's so much overlap? And here's a graphic that kind of shows just kind of how complicated it is. I'm sure you've seen it before, right? Mm-hmm. So these categories that we give these objects in space, we have planets, we have satellites, natural ones, so moons basically, we have dwarf planets, and then the minor planets here are asteroids, and then there's lots of different components, there's comets in that too. So how do we really separate comets from dwarf planets or minor planets like asteroids? I know you said that there's some hybrids, mm-hmm. but for instance, is there a size minimum? So we look at orbit and composition, but is there a size minimum? For instance, when something becomes an asteroid and is no longer a meteoroid out in space?
There's not a well-defined lower limit. For asteroids, we're kind of limited by what we're able to see. And for the ones that get really close to the Earth, like the ones at the very beginning of the show, those are tiny, just a couple of yards, a few meters across. So we call those asteroids just because we were able to see them. There are probably millions of those meter-sized asteroids in the asteroid belt. We're probably never going to see them from the Earth. So for that reason, there's really no lower limit to what we might call an asteroid. Once they enter the Earth's atmosphere, we know that there was something there. It was probably too small for us to see in telescopes. So that ends up getting called a meteoroid when it's out in space. Otherwise, the classifications that you see on the screen right now are largely based on the orbits they follow around the sun. Except for comets. Comets, they show active behavior when they get close to the sun. So gas and dust is released from the surface of the comets. That's why they grow those tails you usually see in pictures. So that's the one easy distinction you can make based on how they look in pictures is an asteroid should not have an atmosphere or a tail coming off of it. Comets would. Otherwise, it's where they are in the solar system, how they orbit the sun.
Great. So Oumuamua that came through, you said that it was maybe made out of hydrogen ices? Mm-hmm. So would those not sublimate or turn directly into gas when getting close to the sun? Because it did get towards Earth's orbit. Mm-hmm. That's kind of the area where a comet would start to sublimate and form those tails or that atmosphere. But did they see that on that visiting asteroid/comet?
Yeah, that's kind of the interesting thing with this idea that's hydrogen ice. They were watching it, of course, to see if there was this activity, and they didn't see any. And that's why it was called an interstellar asteroid. But you watch its path through space, and it seems like it was moving a little bit faster on its way out than it would have if it hadn't had any gas coming off of it. And, if a jet of gas is coming off of a comet, that's going to change how it moves through space. So they've been looking for an explanation for why it had this change in speed. And that's kind of where the hydrogen ice idea comes from, because yes, the hydrogen ice would definitely sublimate. It would turn into a gas, and that might change Oumuamua's speed. But this really thin hydrogen gas would be nearly impossible for us to detect. It's just pure hydrogen. So it could have been releasing hydrogen gas, but we wouldn't have been able to detect it.
Yeah. So if you're just joining us, our guest is an astronomer from the Science Museum of Virginia. If you have any questions about asteroids, you can put them in the chat. There's a little bit of a delay, but we'll try to get them answered. But I have a question for you, Justin. What's your favorite asteroid name?
Ooh, my favorite asteroid name. Um, Again, there's 23,000 to choose from, so that's hard to pick one. I don't know. One of the silliest ones, I think, is Potato. There's an asteroid named Potato, and it's pretty much exactly why you would name an asteroid Potato. What do most asteroids kind of look like in pictures? Lumpy potatoes. So that's why they named it that.
That's great. If you could name an asteroid, do you have one picked out?
Ooh, if I could name an asteroid. I mean, personally, I thought I had a pretty good idea for the object that the New Horizons spacecraft flew by in the Kuiper Belt. This again is when you get into that, what we call these things, is that technically an asteroid or Kuiper Belt object's different, but that's probably a different show. And I thought it was some mythology that kind of worked. It gave it a relationship to Pluto with the flyby by New Horizons. That would have worked. Now that object is called Arakoth. Great name for it, also honoring the indigenous peoples of the Maryland area where the New Horizons mission is operated from. But I thought Iacchus would have been kind of a cool one. It was one of the key holders for Pluto in Greek mythology, and so flying by an object, if it had gotten the name Iacchus with the same spacecraft that visited Pluto, kind of key to understanding the Kuiper Belt. That would be kind of neat. But I guess I've got to find I got to find a new pet project though, because that one's not happening.
Yeah, unfortunately, there's always more things to discover and to name out there. So. All right. Well, it looks like there's no more questions coming in right now, but if you are watching this later, if you think of a question later on, you can drop it in the chat. But thank you, Justin, so much for, again, spending your time with us this Friday morning. We really enjoyed it, and it's definitely inspired me for our next presentation. So I'm going to actually be giving the next presentation here for Your Universe series. We're exploring Jupiter next week, and I'm going to be talking all about Juno at Jupiter. We did this presentation in the dome, so we have a lot of great content, a lot of great visuals that we'll be able to transfer onto the computer and present to Facebook Live. So I'm looking forward to that. Lots of people Jean is saying thank you to Justin. So John as well. So lots of thank you so far in the chat. I'm sure more are coming through.
Great. I appreciate it. Thanks for having me.
All right. Well, take care, everyone, and have a great rest of your day and enjoy your weekend.